Hello everyone, thanks for joining the NTA conference. This is Fatemeh Norouzi, the PhD student at Morgan State University. This research is about the new study of Caputo fractional order financial system. And I did this research with my advisor, Dr. Gaston Gerkata, from the Department of Mathematics at Morgan State University. As the introduction and motivations, I would like to talk about the fractional calculus, which has been so popular recently, and it can be more accurate models rather than the standard derivatives because of their non-local nature. Also, they can cause us memory and chaos in themselves, so it can be used widely in many fields such as science, in different parts of finance, physics, and biology. So in our research, we are interested in the finance model governed by a fractional order capital type fractional. So here we want to prove the existence and the uniqueness of the mild solution, and then we examine the stability properties and the behavior of the equilibria of the system. So if you look at the equations 1, which is the system of the is the usual derivative of the finance system. So here A is the saving amount, B is the cost per investment, and C is the elasticity of the demand of commercial markets. And all of their three different constants, A, B, and C, are the real numbers. So if I want to just recall one paper by Chen, I was motivated by his research because he examined the two most attractive characteristics, which are memory and chaos in the financial system. So he described the financial systems by a fractional nonlinear model, and he showed that chaos exists in fractional order financial system with orders less than 3, and he did the numerical simulation regarding that. In our research, we are interested in the finance model governed by a fractional differential equations, especially in Caputo sense, which is a special case of fractional calculus. So we first prove the existence of solution, and then we examine the stability properties. Our aim is that if we go back to equation 1, if we replace the usual derivative by the Caputo sense fractional derivative of order alpha between 0 to 1, we can have system 2 with all the non-negative initial conditions x, y, and z to be greater than 0. First of all, I would like to recall this theorem by Lizama and Gerkata, which is about the mild solution of the Cauchy local Cauchy problem. So if you consider the system 3, and d alpha of t denotes the Caputo sense derivative, and if we integrate this system with the local conditions of u0 to be x0, we can have the equivalent Volterra equation as equation 4, such that A is a closed linear operator on X. So in our research, by using the theorem 1, which I just mentioned, we consider the initial value problem of system 5, and d alpha of t is the same as before, is the Caputo sense with alpha between 0 to 1. So here we can have the function fi of x1, x2 up to xn, where t is between 0 to t, within the local conditions of xi of 0 to be x0i. The above problem can be written as d alpha of xt to be equal to f of xt, and t and the local conditions are the same as equation 5, the system 5. By using theorem 1, we can obtain the equivalent equation, which is xt to be equal to x naught plus I alpha times f of xt. So if we make these assumptions as h1 and h2, and we can have all the functions f to be continuous on the subset D, closed subset of Rn, and if we have the Lipschitz conditions of f such that the norm of f of xt minus f of yt to be less than L times the norm of xt minus yt, we can prove the following theorem, which is about the existence and uniqueness of the merged solution. So under these assumptions, we can have such that L omega to the power negative alpha to be less than 1, we can prove that there exists a unique solution on the initial value problem 6 that we have here. This is the system 6. So if we go to the proof, we consider the map omega on D, and we know that omega is well defined in the view of equation 7. And if we do the calculation on the norm of e to the power negative omega t times omega x of t minus omega y of t, after doing some calculations, we can get L times the norm of x minus y times 1 over omega to the power alpha, which is the norm of the initial one is less than this amount. And since as the assumption we have L over omega to the power alpha is less than 1, we can resolve that omega is the contraction based on the Banach fixed point principle, and therefore we can have a unique merged solution to the system. So until here, we prove that there exists a unique solution. Now, regarding the stability conditions, we are interested to have some conditions on the global stability. So we need the equilibrium points on the 3D surface. By making all the equations of system 2 to be equal to 0, we can get the equilibrium points E0, E1, and E2. And here E0 is clearly not on the R3 surface, so space. So we only consider E2 and E1, and based on the equilibrium points, we can have the Jacobian matrix based on each of them, and by using Cardano's formula, we can obtain the stability conditions based on each of the eigenvalues. So here I just give an example based on the Jacobian matrix of the system to evaluate that E1. We can have this Jacobian matrix, and if we have delta to be q over 2 to the power 2 plus p over 3 to the power 3, we can have 3 different options: delta to be positive, to be 0, and to be negative. If we have delta to be positive, the cubic equation has 1 real and 2 complex conjugates. If we have 0, then the equation has 3 real roots, and at least 2 of them are equal. And if we have negative, the equation has 3 distinct real roots. So we can have the solution of the system to be x by the conditions p and q. So therefore, the eigenvalues corresponding to the Jacobian matrix of the equilibrium E1 would be lambda to be equal to 3x minus b plus c minus 1 over 3. and we can resolve the stability conditions based on the eigenvalue. So if we have the conditions to be stable, asymptotically stable, and unstable. At the conclusion, we considered the fractional order finance model in the sense of Caputo type derivative, and we investigated the dynamical behavior of it, and we proved the existence and uniqueness of the solution by one-off fixed point principle, and the stability properties of the solution was investigated in the 3D plane. And I would like to be grateful of the School of Computer, Mathematical, and Natural Sciences for the financial support at Morgan State University. And these are all the references mainly which I used in my research. And thanks for the attention and joining the NTA conference. Have a great day.